Welcome to section 4.5 of M1. This is the part of circular motion where we look at problems that are in 3D. So basically we're looking at things that are moving vertically, whereas previously they were moving possibly on a flat surface. So for motion in a vertical circle, the component of the acceleration r omega squared towards the centre of the circle, and it's r theta is equal to v. Okay. So that's one of the postulates, or one of the ideas that we're using. Here's the second idea. Here's the third. Here's the fourth. Those are important, so you might want to make notes of each of those. Okay, so let's start by looking at a simple example. Okay, so this is a particle. Its mass is 0.6 kilograms and it's attached to a light rod. So the rod is free to rotate vertically, okay, about this central point B. So how is this working? Well, we're looking at something that's free to rotate as it is on the screen. Okay, this is the vertical plane, and so you're asked to look at the speed of the particle as it passes through the lowest point of the path. This is pretty easy to do because as it loses potential energy, or gravitational potential energy, it'll gain kinetic energy. So it's basically just going to fall through 0.5 meters. And that potential energy gets turned into kinetic energy, and so as it falls 0.5 meters, we end up with this mgh is equal to half mv squared. So the potential energy gets turned into kinetic energy. So here's gh, okay, it's half a meter times by 9.8, and that's equal to half v squared. So the mass cancels, so it's very easy to rearrange, and we get that the V is 3.1 meters per second. Find the tension in the rod. So the tension in the rod obviously is inwards, okay, towards the centre of the circle, providing a centripetal force. So there's a centripetal force that's causing the acceleration, and the mass is down, okay. So what we have is that the total centripetal force is equal to mv squared over r, and that total centripetal force is the tension. Take away mg, so mg is an extra force. Okay, so here's the centripetal force. You could look at it as another way. Tension is equal to the centripetal force plus mg, and it doesn't really matter which way you do it. But if you look at the centripetal force inwards, mg, tension is inwards, mg is outwards. So either way you look at it, this equation is the same. So using the idea and the equation for centripetal force, it's easy to find T. Okay, here's mg, here's the centripetal force, and so those two values give us a final answer of 17.64. So that's a nice simple example, and we'll move on to a slightly more complicated example. Okay, now this question, I'll just let you read it. I'll pause the video to read it. This question is getting us to look at a similar situation. It's the tension in the string at a particular angle. Now, when you've got your angle theta, it's a nice problem because the skills involved in this problem getting you to be able to solve any problem. So it's a really good question, really good example for you to have a look at. So we set some initial conditions with our initial potential energy. We set it at equal to 0 here, it just makes it easy. It starts off at 0, it's a good start value. Now obviously we have an initial kinetic energy because it's projected vertically downwards with speed root gr. So if we square the velocity, then root gr squared just makes gr. Okay, so we've got kinetic energy half mgr. Okay, so when OP is theta degrees below the horizontal, the tension, we need to find tension speed basically. Now, it'll have tension T, it'll have speed V. So if we look at the potential energy, there's a loss in height, okay? And as the height goes, as it drops down, that potential energy, that loss in potential energy, gets converted into kinetic energy. So despite the fact that we said that the initial potential energy is 0, we can now say it's just a negative, okay? It's fine. So, any loss in potential gets converted into kinetic. So if you equate those together, then you can rearrange and you can say, well, the total energy is now any potential that's converted into kinetic plus any potential gets converted into kinetic. Looking at that, we set up this equation here, and obviously we've got a common m that we can cancel. We can get rid of this half here, and that cancels with a half here. So we get that gr is 2gr sine theta, so that's equal to v. Okay, so this gives us a value for v squared. And this value for v squared we're going to use to find the centripetal acceleration, or the centripetal force, rather. So the centripetal force is going to have an effect on the tension. So, the idea: drops in height, gains kinetic energy, increases in speed, increases in centripetal force. So, this velocity is useful. So towards O, we have T is equal to, we got the tension, take away a component of the weight. Okay, so mg sine theta is our weight component here. That's equal to mv squared over r. Okay, so we can look at that. We've got these here. So this is mv squared over r, and we can carry on with that equation and we can rearrange it, and we've got an equation for t. Okay, so similar to the original question we did, the first easy example, we've got tension in this direction. Okay, so tension's in this direction, take away a weight component in this direction is equal to the centripetal force. Okay? Or the other way to look at it is tension, which is in this component, is equal to the component of weight that's going in this direction and the centripetal force, which is going, obviously, trying to move in this direction, so the tension has to go in the opposite direction to the momentum, if you like, of the object. So, we've got two terms here in mg sine theta. We've got mg here, and we've got more sine thetas here. So this term will simplify, and obviously it's a force, so you've got to put the final answer is in newtons. Okay, so that one is a little problem. Have another look through it, see if you can work out what I've done. Okay, and then the second part of the question asks us to look at it snapping. So we take that value of tension, okay, we say, well, it breaks when it's, so that information is given in the question originally, when the tension is 2 mg, so you just set 2 mg equal to T, you've got the rest of the question here, okay, and then you get a nice little sine theta, you get an angle, so you can very easily find an angle for when the string will break. So the question led you into that. So B isn't worth anywhere near as much as A. Okay, all the thinking is in A, and then you're just applying your formula to B. Okay, so I'll just scroll down and let you have a look at the workings. Very, very simple for M3 level. Okay, 2mg is equal to mg. 1 plus 3 sine theta. The mg's cancel. Rearrange it. Move the 1 to the other side. Okay, so you've got 1 is equal to 3 sine theta. Move the 3 to the other side. 1 over 3. And then sine to the minus 1 gets rid of the sine to give you theta. Okay, so theta is 19.5 degrees. Okay, so hopefully this has been an okay to understand topic. Have a look again at the video. Okay, make sure you're familiar with all of the points that came in the first slide, because you could need to use any one of those ideas, and then those ideas get used for the next section as well. Okay, good luck.